Thank you so much. So I'm Martin. I'm from Korea, from KAIST, the Advanced Institute of Science and Technology. And this is joint work with Aras Paho from Caltech. Actually did the whole heavy lifting of the technical groups, which I'm not going to present or to Aras. And instead, I'm going to focus on the motivation and the overall framework. So this is my second time attending this conference series. Last time I talked about our vision of developing a computer analysis system, kind of a counterpart to computer algebra system which solves differential equations reliably. Kind of like MATLAB, but MATLAB is known to produce garbage in many more or less artificial examples. And we work on developing a rigorous foundation to such a computer analysis system. For example, thanks to Svetlana over there, we now have a rigorous characterization of the computational bit complexity intrinsic to linear partial differential equations. Basically, partial differential equation with, let's say, polynomial time computable coefficients and polynomial time computable initial condition, the solution can go up to P space, but not beyond. And if the conditions are promised to be constant, then the solution remains within short P, and that's also best possible. So complexity here refers to bit complexity, the cost, achieve uniform approximation of the error 2 to the minus n. Uniform approximations means we're talking about continuous solutions, right? Space of continuous functions. But many PDEs live more naturally in Sobolev spaces. Right? So after these great results, we try to apply or adapt this to the Sobolev setting, but we realize there is no definition of computational complexity for functions in Sobolev space. And while that's not true, there are actually two definitions, natural definitions for computational complexity of function living in a Sobolev space, or let's keep it simple, L2 space of square integrable functions. Now, you may know the saying, a man is one watch knows what time it is. A man with two watches is never sure what time it is. Right? Seagull's law, it's called. And we were in such a situation, right? We had two definitions, and they had been shown to be equivalent with respect to computability, so qualitative, but with respect to complexity, quantitatively, we were not sure whether they're equivalent, and if not, which one to use. And this is maybe similar to the setting of early days of computability theory, say 1940s, where there were three definitions of what is a computable integer function. This definition is a new recursion going back to David Hilbert. Right? Second definition based on Turing machines. And third definition, lambda definable in terms of lambda calculus. At that time, any results showing that some function be computable or uncomputable had to refer to one of the three definitions until Rosser came along and showed that they're all equivalent, and this gave a boost to computability theory, right? Because from then on, people could only refer to computed or uncomputable was all without this qualifier. And hopefully we achieve the same for complexity theory of LP functions in LP space. So, 2020, together with Svetlana and Donjun, we asked the question, what is a polynomial time computable L2 function? Asking for a definition, and of course, should be a well-justified definition, not just a top definition. And ideally, several definitions shown to be equivalent. This is usually evidence that it's a reasonable definition. So today, I'm going to recall, 2/3 of my talk will be on background, and the last third will be about the actual contribution. So I'm going to recall computational problems, importance of parameterizing problems in order to even define the computational complexity of such a problem, beyond the discrete case, talking about continuous setting. I'm going to recall the easy case of compact domains, then generalize to sigma compact domains, that is counted units of compact sets. Then generalize that parameterization to compact monotone covers. First and second order parameterizations. I'm going to explain that. Then I will recall the case, the well-settled case of parameterizing the space of continuous functions, which is not sigma compact and therefore requires second order parameterizations. And there are two major second order parameterizations, one in terms of the modulus of continuity, and the other in terms of the Weierauch degree. And I will recall them and then recall that and in what sense they are equivalent, and therefore there's a common notion of computational complexity for continuous functions operating on spaces of continuous functions. And then finally, I'll get to the LP case with three parameterizations: LP modulus, LP step rate, and LP Fourier rate, which is short for rate of convergence of Fourier series and rate of convergence of step functions. And our main result is that these three are linearly equivalent in a sense that I'm going to explain, meaning that any three of them can be used to define computational complexity up to linear and particularly up to the polynomial perspective. So let's start with looking at, and by the way, yes, I'm going to adopt two perspectives. One is the maybe more common binary perspective, which corresponds to the binary lengths of integers, and the other is the unary setting, which corresponds to the lengths of integers encoded in unary, and generalize that. And I'm not going to take sides, so whenever you see something in green, it refers to the binary complexity parameter. When you see something in red, it refers to the unary complexity parameter. Okay, computational problems. So, computational problem has a space of inputs and a space of possible outputs. And examples are testing whether an integer is prime, whether input are natural numbers, and the output is a Boolean, yes, it's prime, no, it's not prime. Factorization, where the codomain is integers, let's say the largest non-trivial divisor. Or graph problems, decision problem as a graph has a Hamiltonian cycle. There the input is the range of all graphs, and the output is Booleans. Moving on to the continuous setting, for example, the exponential function, the real line, input space reals, output space reals, or the complex plane. For compact setting is when we maybe restrict to the unit interval real and then corresponding output interval. When we consider definite Riemann integration, the input space is a space of continuous functions. The output is a real number. Indefinite Riemann integration, the output space is also function space. And what we're aiming at is the wave equation. Here you see the partial differential equation for the wave equation, which we did consider with Svetlana in a space. So the initial condition here is a space of continuously differentiable functions. Oh, that's not with Svetlana. Sorry, that was Weierauch. report that in a second. And the solution is also in the space of continuous function, but that's not appropriate setting because the wave equation is not well posed in the sense of Hadamard in this setting. The right setting is, as pointed out by Heuhoff and Song, is Sobolev spaces. And this is where we started off, trying to define computational complexity of Sobolev spaces, or to begin with LP spaces. And you may notice that there is two types of computational problems. One is discrete, and below the red line, these are continuous. And this basically means that the input and output are finite or infinite. And one can usually approximate the continuous output. So replacing the space, the real interval with the rationals and introducing a new error parameter for the input. So the goal is to approximate the solution or the exponential function up to some error parameter, which is an integer. And in this case, the output is finite, and we talk about terminating algorithms, not type 2 machines. So finite output, and same for all the other types of problems. And there are two major perspectives on the error parameter. One is unary, approximating up to error 2 to the minus n. No, that's the binary. And the unary is approximating up to absolute error 1 over n. So let's record reports of parameterizing problems, both in the discrete and in the continuous setting. So integer factorization is hard, right? RSA is based on it, because we don't know how to do it. Define polynomial in the binary input length. So that's the binary parameter, which is basically the logarithm of the value of the integer we want to factor. Another perspective is unary perspective. There, factorization becomes polynomial time computable ABC of Eratosthenes, right? So I don't take sides for either one, I just report that and generalize that for the continuous setting. So the difference is exponential difference between both parameters in order to define computational complexity. You can also consider the decimal input length as a parameter, but of course that changes only after the constant vector. So there's a linear relation between these two complexity parameters. And this is kind of a prototype of the result that we obtain, that we prove for the case of LP spaces. So linear relation between these two parameters, exponential relation to the unary parameter. For graphs, usually one considers the number of vertices as input parameter, or the size of the adjacency matrix. Between these two parameters, there's no linear, but a polynomial relation. So as long as we're interested in polynomial time complexity, that's good enough. Only when we want to look more closely, then we want linear relation between parameters. So now consider the problem of calculating the exponential function. We have introduced this additional error parameter, which means we want to approximate the exponential function up to absolute error 1 over n, or we want to approximate it up to error 2 to the minus n. This is what I will refer to as binary approximation, which is basically the logarithm of 1 over epsilon, the absolute error. And similarly for the other problems, again, we have this exponential relation between the two parameters, and this carries over to all the other problems. So the importance of fixing a certain parameterization, two major classes being unary or binary, and the difference between binary and decimal is only linear. Difference between unary and binary is exponential. So now let's move on to problems defined over compact domains. And the observation is, which is obvious and not even stated in textbooks on computational complexity, is that it is well defined for an algorithm which is promised to terminate everything everywhere. It is well defined to consider its worst case complexity inputs up to length n. Why? Because it's a finite maximum, right? The worst case, when you take the running time of the algorithm of all inputs up to size n, that is up to value 2 to the n, each running time being finite, maximum finitely many. This is the usual definition of worst case complexity, and then nothing n tend to infinity, that's asymptotic complexity. Same for graph algorithms, right? Consider algorithms running time on all graphs up to n vertices, first case, and then n range. So, and the observation is that these finite restrictions, all graphs of up to n vertices or all integers up to 2 to the n, this is finite, and finite is the same as saying compact in the discrete topology. And this, I say this because this is a way to generalize this to the continuous setting. Because it's a well-known folklore effect in computer analysis that the same holds true even in the continuous setting as long as the domain is compact. So when we have continuous inputs, any algorithm that is guaranteed to terminate on all real numbers in this compact interval will have a worst case running time. That's a continuity argument. So what can define the worst case running time? And this is going to be a finite integer, right? There are no parameters here. Whereas if we consider the algorithm of all real numbers, the maximum will not be exist in general. So this is why in our paper, generalized the ACM, focus on coding and complexity zero compact metric spaces. But most spaces are not compact, right? So the integers are not compact, but they are sigma compact. And this is why there's this additional parameter focus restrict to compact subsets, and then that the compact subsets exhaust the entire integers. And the same we can do here. With the real numbers, there are two natural ways of exhausting it with compact sets, either with intervals of size 2 to the k, binary parameter, and then the maximum will be well defined, and we can consider asymptotics with k running to infinity, or we can do the same in red with unitary complexity parameter, and then let that run to infinity. Now, as I mentioned before, usually in this discrete setting, we want to approximate the output, so that's why we added this additional error parameters n. So now we have actually two parameters. One is the approximation error, which can be binary or unary, and the other is the parameter which to restrict the domain to some compact subsets. And then we get a whole bunch of complexity definitions, binary depending on approximation error, unary depending on approximation error on compact domain, and on sigma compact domain, all four combinations made reasonable. Okay, so that covers the case of sigma compact domains. And let's see what is the common scheme behind them. It's compact monotone covers. Okay? So for compact sets, you don't need any parameters. And when the space is not compact, we cover it with increasingly large compact sets, and then see how the complexity grows as we run through these larger compact sets. On compact monotone cover. So here's a gist of that. Fix a topological space in a directed set, which serves as the parameter space. And compact monotone cover is a mapping from this index set to the power set of the space, which maps actually to the compact subsets of the space. It should be monotone, so larger arguments should reflect to larger sets, and it should cover, so the union should be everything. And the examples we just saw are fit into this scheme. So for the natural numbers, we had this compact monotone cover where the index set is just the natural numbers itself, or binary or unary. Same for graphs, the index set is the natural numbers. When we talk about exponential functions on the real line, we actually have two parameters, right? This means that the directed set, the index set, is now a Cartesian product, which is not totally ordered, but it's still a directed set, partially ordered set. Yes. So this covers what we've seen so far, but our goal, our next step is to proceed to the space of continuous functions. And the space of continuous function is not even sigma compact. And that's, we need to step up from first order parameterizations, natural numbers or pair of natural numbers, to non-decreasing functions of natural numbers. That's what we call second order parameterization, or step up. So let's recall about continuous function and modulus of continuity. So the space of continuous function, even if we restrict to compact domain and compact codomain, is not sigma compact. So it's not out union of compact sets. But according to Arzela-Ascoli, we know how the compact subsets look like. And these are characterized by uniform continuity, modulus of uniform continuity. So this is a subset where mu is a modulus uniform continuity. Let me recall for you what is a modulus of uniform continuity. It's kind of the schemarization of the epsilon delta definition of continuity. It says if the arguments are sufficiently close as described by the modulus, then the values are guaranteed to be sufficiently close. So this is again green, small letters, binary setting, everything to the power of 2 or 1 over 2. And yeah, this is a well-known notion. There's also a counterpart, unary counterpart, where we have error 1 over n. Seven. So popular notions of continuity, like Lipsch's continuity and Helder continuity, can now be rephrased in terms of this asymptotic growth of this moduli, or can translate between binary and unary moduli with this in the argument and in the value, right? So it's because the modulus is an integer function, and there are explicit examples of functions which have exponentially large binary modulus. Basically, this function is very steep, but it is still continuous here even at 0. And this translates to computational complexity intuitively. Here we need to know the argument very precisely, and that takes a lot of time to process in order to produce the value even with modest precision. So that's a justification of the modulus of continuity, because it's known to be related to computational complexity, and modulus of continuity is one way of parameterizing the space of continuous function. According to Arzela-Ascoli, each of these subspaces is compact with respect to the uniform norm, so satisfies this property, and also any compact subset is contained in some leaves of space, so together they cover the space of continuous function, and that's why modulus of continuity is the common way of parameterizing computational complexity on the space of continuous function. Now, there's another way, that's in terms of Weierstrass approximation theory. You may recall that any continuous function on the, let's say, compact unit interval can be approximated by polynomials. What degree do we need for a polynomial to approximate up to some certain error? And gives rise to another modulus. Right? And let's call this the Weierstrass modulus. Here in the binary version, there's also a unitary version. Binary meaning everything is an exponent to base 2. And yeah, as I said, Siegel's law, 2 definitions, which one should be used. Fortunately, it doesn't matter because the 2 are linearly related up to some constant f set in the argument and in the value. So that's why in the complexity theory of operations on the space of continuous functions is so well established because there are 2 equivalent definitions which we can switch back and forth. So that's almost there, stay with me. So we've talked about computational problems, parameterizing problems, compact domains, sigma compact domains, modulus of continuity in Weierstrass degree as equivalent, linearly equivalent ways of parameterizing the space of continuous functions. And now final lab, Lp space. So let's try to generalize modulus of continuity from the Arzela-Ascoli theory. And the way of generalize Arzela-Ascoli is so Lp spaces are also not sigma compact. And way to generalize here is to see the hierarchy of Lp spaces, which contains the space of continuous function and common parameterization due to textbook of Précy and my former PhD student Florian is use of Lp modulus. Lp modulus is in a sense a counterpart to modulus of continuity in the sense that modulus of continuity according to Arzela-Ascoli characterizes compact subsets of continuous functions and Kolmogorov characterizes compact subsets of the Lp space in terms of the Lp modulus. So Lp modulus basically says if you shift the function sufficiently little, then the norm of the difference will be small. So yeah, it's kind of like modulus of continuity, but now with the Lp norm and with a shift. So is this a good parameter? Florian used this in a paper, but it didn't take off because I'll justify that apart from this correspondence between Arzela-Ascoli and Kolmogorov. Here's another parameterization that is found in the literature, rate of convergence of a Fourier series. We know Fourier's coefficient, right? Well defined on L1 space, all spaces. And then we can write a Fourier series. And it turns out that the Fourier series converges to the original function, not just in the L2 case, which is common, but also for the other spaces, except for the boundary case p equal 1 and p equal infinity. And we can ask how many terms of this Fourier series we need in order to approximate the original Lp function up to error 2 to the minus n. And let's define this to be the binary Fourier rate. That's our second parameterization. And the third parameterization, equally naturally, arguably, is approximating by step function. You know, step functions can be used to approximate Lp functions. So how many of these steps do we need to approximate a given Lp function up to error 2 to the minus n? And that's our definition of the binary step rate. How many steps? And now we are there. Now we have the three parameterizations, second order parameterizations, not in terms of integers, not in terms of integer pairs, but in terms of integer functions. First one being the LP modulus, second one the rate of convergence of Fourier series, third the rate of conversion of these set functions, and our theorem says that all three are linearly related. So that means as long as we're interested in polynomial time complexity, any of these three can be used. Even if we're interested in linear complexity, they are also equivalent. Only if we want to look more closely, then we do need to look more close. So that's, I'm out of time, right? So let me skip the remarks and examples and conclude with this slide. Thank you very much for your attention.